Welcome back. Well, we're down to our last lecture of the semester on correlation and regression. Now, your textbook covers this topic very early on. I choose to cover it last for various reasons. I think that this is that it really can be covered either way, but I think that there's a logical progression from the earlier topics that I've covered, Z to T to F. I really think those follow a certain logic, and it makes sense to keep these concepts, correlation and regression, for last. Although, as your book describes quite well, ANOVA and correlation and regression, they fall within this general concept of general linear modeling, which is something important to remember. But a lot of these statistics do have an underlying relationship based on an underlying model. But let's go ahead and dive in here. Correlation and regression. They both examine linear or straight line relationships. Both work with a pair of scores, one on each of two variables, x and y. So we're going to be seeing lots of graphics here today, scatter plots as they're called, where you have your x-axis and y-axis both depicted. So correlation and regression, very related subjects. That's why I'm covering them both in the same lecture here. Although I do have it broken down a bit, separated a little bit in terms of the semester here, so you have enough time to absorb all the information about these. Well, correlation is the degree of linear relationship between x and y. It's measured or described by the statistic R. Regression is a little different. It has to do with prediction instead of description. So correlation kind of describes a relationship. Regression is all about prediction. So regression is concerned with predicting y from x. All right. So the example I'll be giving is quite a common one, where college admission boards are going to look at ACT scores and SAT scores, and one goal of theirs might be to try to predict a student's college GPA based on their ACT score, let's say. And so if you're doing that, well, you're going to be using regression, okay? Regression forms a prediction equation to predict y from x, and it's an equation you will have to memorize, a very simple equation, okay? But first, let's get into correlation. Correlation is the aspect of the data that we want to describe or measure, and it's a degree of linear relationship between x and y. The statistic R describes the degree of linear relationship between x and y, as I already mentioned. And here's the formula. R equals the summation of the z-scores for x times the z-scores for y divided by n. Okay, in other words, R is simply the average product of z-scores for x and y. So, x and y are typically going to be different measures. So you're taking the ACT measure and you're trying to predict the GPA measure. Maybe you're arguing that they're both measures of intelligence or academic success, and so one should predict the other. But they're on different scales, okay? So the ACT scale is quite different. It goes from 0 to 36, from the GPA scale, typically from 0 to 4.0. Because they're on different scales, you want to eliminate that distraction by putting them on the same scale. Put them on a Z scale. Okay, Z is the common way of doing that, by just equating measures, putting them on a Z scale, making it any differences in scores based on differences in standard deviation from the mean. Okay, and that is what Z scores do, as we've already learned in this course. So R works with two variables, x and y. R ranges from -1 to +1, so it measures both positive and negative relationships. We'll see examples of that in a moment here. It measures only the degree of linear relationships, so you have to have a linear relationship between variables. It can't be non-linear, and I'll give you an example of what that looks like. I mean, there could be a variety of relationships that exist. You can have a curvilinear relationship that can have different forms. I'll give you an example of that. Rsquared, also very important to remember. It's simply squaring the R value. It gives you the proportion of variance or variability in y that is explained by x. Okay, so if you find a a nice positive correlation between ACT score and college GPA. Let's say you get a correlation of 0.6. That's pretty good. R ranges from -1 to +1, and you have a 0.6, so that's pretty close to +1. That's pretty good, pretty strong relationship there. Well, you take 0.6, you square it, and you get 0.36. That tells you that ACT scores are accounting for 36% of the variance in GPA. I don't think that is actually the relationship between the two. I would be surprised if it were that strong, but that would be very powerful. That would say essentially that, hey, 36% of variance in GPA that you get among all your students can be accounted for, can be predicted by their ACT scores. Okay, that would be quite powerful. R is undefined if X or Y has zero spread. Okay, so you got to have some spread. You have to have some standard deviation for X and Y in order for this to make any sense, really. Okay, so let's look at some scatter plots here to picture this. So the sign of R shows the type of linear relationship between X and Y. We can use the definitional formula for R and the scatter plots to see positive, negative, and zero relationships. So here is exactly what it would look like for an R of 1, where you have X, of course, down here, Y on the vertical axis, and that's always how it is. X is on the horizontal axis, Y is on the of course on the Y axis, Y is on the vertical axis. And here's a perfect linear relationship where for every increase in Y, you have a concurrent increase in X, and vice versa. That's a perfect one-to-one relationship, and it's positive in this way. Negative, this is also a very powerful relationship, but it's negative in this case. So for every increase in X, you actually have a decrease in Y. Okay, so that's called a negative relationship, where one moves up, the other one moves down. Positive simply means as one moves up, the other one moves up, and as one moves down, the other one moves down. So if they're moving in the same direction, it's a positive relationship. If they're moving in opposite directions, it is a negative relationship. And this is just a depiction of R of 0, where you don't have any predictive ability of X to Y or vice versa. Okay, so this is just to point out that, again, correlation is all about linear relationships, not curvilinear or other types of relationships. So here is what looks to be an interesting curvilinear relationship here. You might get this. This is called the, one way of describing this is the Yerkes-Dodson law, such that, let's say you have stress levels on the, let me describe this a little differently here. Let's say you have stress levels on the y-axis, and you have, okay, let me start over. Stress levels on the x-axis, and on the y-axis you have memory ability. Okay, so let's say it's an eyewitness to a crime, and lower on the x-axis you have hardly any stress. Let's say they're just sleepwalking, hardly awake at all when a crime takes place. Well, their memory for what the perpetrator looked like will be quite low. And then all of a sudden you get to the middle, and hey, they're awake, they're alert, they're absorbing what's going on, they're going to have a pretty decent memory of what the guy looked like, the perpetrator. But then as you get to higher levels, the perpetrator's waving a gun in their face, they're going to be really stressed out, highly anxious. Yeah, sure enough, based on the Yerkes-Dodson law, you find that their memory for the perp's face actually gets lower there. So that is a curvilinear relationship between stress or anxiety and memory. Okay, there's all kinds of other curvilinear relationships out there, but that's the one I'm going to use as an example. Well, you don't want to use correlation in that case. It's not going to be revealing. It could give you a 0. Okay, it could be giving you the same as this kind of amorphous mass of data points here, where it doesn't reveal anything about this. It can completely miss a curvilinear relationship. So you don't want to use R in that case. Rather, you want to use R whenever you have any kind of a linear relationship that can look like any one of these. Okay, and these are all positive relationships, but you can have these negatively as well. R², as I pointed out already, is the proportion of variability in Y that is explained by X. So if R is 0.5, which is shown here, then R squared is 0.25, and that's the proportion of variability in y that is explained by x. In other words, 25% of y can be explained by x, which still leaves 75% unexplained, but still a single factor, x, if it explains 25% of the variance in y, that's pretty good, that's pretty powerful. Okay, it would be, again, this kind of form here. But here's an even more powerful correlation, 0.7, and R squared, or variance accounted for, is 49%. And here's 0.9, as you know, it's getting close to that higher limit of 1, so R squared is also going to approach 1. 81% of variance is explained by this relationship. Very, very powerful relationship here. You don't often see that powerful of a correlation, but to give you an example of when you might see that, you know, height and weight are related pretty strongly in this way. I would say it's probably pretty high, like a 0.9 relationship there. As height goes up, weight tends to go up as well. In terms of Venn diagrams, you can really nicely illustrate R squared, okay, the proportion of overlap between y and x. Okay, so x and y, x can account for the amount of overlap with y. Okay, about 25% of y is accounted for by x. Here it's about 50%, 49% of y, and here it's a whopping 81% of y is accounted for or overlapped with x. Okay, but you still have this amount unaccounted for here, 19%. Okay, so what is undefined here? This is just some additional information on the fact that, hey, you have to have some variance. You can't ever have a, you can sometimes find a relationship like this, but you can't use R. You can't use correlation to define this relationship if you have zero variance in y, which is what I'm depicting here, or zero variance in x, which is this right scatter plot here. Okay, you have to have some variance. That's the only way you can use z-scales and find this correlation R. And I think this is my last slide on correlation, just pointing out the population correlation coefficient. There's always a parameter to go with each statistic, so the statistic R goes with rho from the population. Okay, so you're trying to predict rho based on your R value, given your samples. And of course, correlation does not imply causation. You've probably heard that before. You know, if you find that A and B are correlated, let's say that you know, ACT and ACT scores for your incoming freshman college students ends up being related to their GPA their freshman year. You know, they're correlated. It doesn't mean, however, that A is causing B, that their ACT score somehow is causing their GPA. It could be that, well, this doesn't exactly work because they differ in time here. One comes before the other. But let me use a different example here. Let's say violent television watching, or violent movies, violent media, and aggression in grade schoolers, okay? There's a relationship there. Clearly, there is a correlation, a positive correlation there, such that the amount of violent TV watching is positively related with the amount of aggression. As one goes up, the other one goes up. As one goes down, the other one goes down. But does that mean that violent television, violent media viewing is causing higher aggression? Well, that's just one of many possibilities. You don't know until you do experiments and you control for these things. If you only have correlational studies, then it could be that, yeah, violent TV watching is causing aggression. It could just as easily be the case that children who were already higher in aggression are just more likely to watch violent TV, okay? Or it could be some other factor, C, that's causing both A and B. Maybe it's just how their parents are raising them, or maybe it's genetics. Parents with, you know, more aggressive types of genes, if you will, pass those on to their children, and so they get children who, you know, want to watch violent TV like their parents did, and also have more aggressive genes or something. Okay, you never know what it is. You just know, strictly speaking, there is a positive correlation or a negative correlation, and that's all you know. You got to stop there. People often want to jump the gun and make arguments about causality just based on correlational relationships, and that's not appropriate. Okay, so moving on to regression. Regression is concerned with forming a prediction equation to predict y from x. So really this makes regression more interesting and practical than correlation. Correlation is just descriptive, whereas regression is more predictive. This is the case where, the example of ACT scores, you're trying to use that to predict something, college GPA for example. Regression uses the following formula: y prime equals bx plus a. Y prime is the predicted y score on your criterion variable. In my example, it is college GPA, that is your criterion variable. The y score is the actual GPA that your student gets at the end of their freshman year. Y prime is what you're predicting that their GPA is going to be. It's unlikely those are going to be identical, but you're trying to get as close as you can to their actual score as you can with the predicted score. But you got to have that little prime value there, y prime, because you're just trying to predict the y score. It's not exactly the y score. B is slope. Okay, we've all seen this before. Rise over run. The change in y divided by the change in x is your b, or slope. X is the score on the predictor variable. So in my example, the predictor variable is ACT score. Okay, you're trying to use that variable to predict your criterion variable. And A is the y-intercept. It is where this line over here is crossing the y-axis, the vertical axis here. Value of y prime when x is 0, in other words. And again, just like correlation, regression is strictly dealing with linear data. You can generalize only for x values in your sample. So if you're trying to predict GPA based on ACT scores, well then you have to acknowledge right off the bat that you're only using ACT scores. You're not using anything else, okay? Even if it might be relevant. You're just saying, well, I'm just trying to do what I can with ACT scores. And let's say that the admission folder comes in for a student and everything gets lost except for their ACT score, so that's all you have to work with. Well, you have to acknowledge that. You're only dealing with X, in this case ACT scores, to predict Y, your GPA score, the student's GPA score, after their freshman year. So, as I pointed out already, actual observed Y is going to be different from what you're predicting, but you're trying to minimize that difference as much as possible. In other words, you're trying to minimize error. Error is what you end up having as the difference between Y and Y prime. Okay, so Y is Y prime plus error. In other words, error in regression is Y minus Y prime. Okay, so if you're, if let's say the student had great ACT scores, so you're predicting that they'll have a 4.0 GPA. Well, your 4.0 is your Y prime, but let's say they end up with a 3.9, okay? Well, then your error is the difference between those, okay? It gives you an idea of what the error is, okay? The fact that your prediction is never going to be perfect. And regression, it's important to realize that there are an infinite number of potential regression lines, but there's only going to be one best fitting line. So this is the last slide I have for you today. The best fitting line, as depicted here, it's the yellow line. The best fitting line is going to be the one that is minimizing the squared difference between each of your data points and basically it's the line that minimizes the differences between your Y's, your actual scores, and what you're predicting them to be. And of course you square it because you're trying to get rid of negative and positive. You want to make everything positive. You want to make you want to make everything positive. That's why you square it. Okay, so the sum of your squared errors equals sum of all the differences between actual and predicted scores squared. Okay, so that would give you this best predicting line here. It's the one that is as close as you can get to defining this linear relationship here. I mean, ideally, if you had a perfect relationship, a one-to-one relationship, then all the data points would fall exactly on this line. But that's not realistic. There's always going to be some variance. There's always going to be some error. And so there's going to be some distribution of your points here, your actual scores. But you're trying to minimize the relationship between predicted and actual scores. So this is called the least squares criterion. That's where I want to leave you here. This is the last lecture for the course. As usual, if you have any questions about correlation or regression after you watch this lecture a couple times, read the chapter, the relevant chapter in your textbook. Try to get a solid grasp on it, but if you still have questions after that, feel free to go to the discussion board for this topic and take your time on this. This is the last topic we're going to cover, and definitely going to be featured on the final exam, so study hard. Well, it's been a pleasure having you in the course and providing these lectures to you. Looking forward to seeing how you do on the final exam, and of course, come to me with any questions you might have.